Welcome to Brain Vision.
To figure out the relationship between the wavelength and the minimum potential difference, delta V, which with an electron is accelerated, we use the fact that the energy, E, of the emitted wavelength is equal to hc over lambda, and the energy of the accelerated electron is equal to the charge of the electron, E, times the potential difference, delta V. So in other words, we have our relationship between wavelength and delta V. For part A, we have hc over lambda is equal to E delta V. Where delta V is the potential difference and lambda is the wavelength, so that is our relationship between the two. Part B wants us to put this relationship into words. So to put this relationship into words, we can say that the wavelength and the potential difference are inversely proportional to each other. Or in other words, if the wavelength gets larger, the potential difference gets smaller. If the potential difference wavelength gets smaller, the potential difference gets larger. So we can say wavelength is inversely proportional to the potential difference. Is the way of explaining the equation for part A. Now, part C says it wants us to look at figure 42.22 and explain whether your results predict the correct minimum wavelengths in this figure. But if you look at this figure, you can tell that that figure is actually plotting wavelength versus the intensity, but our equation gives us wavelength versus potential difference. So we can say the figure plots X-ray intensity versus wavelength, not potential difference versus wavelength. Thus, the figure and the solution in part A, I spelled the figure wrong, are not related. Right, so the figure is intensity versus wavelength, but our relationship gives us potential difference in wavelength, so they're not related. Part D wants to know if our equation in part A applies to other parts of the electromagnetic radiation besides X-rays, but by definition, no, this only applies to X-rays. So we can say no, by definition, this only applies to X-rays produced from an accelerated electron through a potential difference. Part E wants to know what happens when we send our wavelength to extremely small values or it approaches zero. What happens to the potential difference? So if we go back up and we look at our equation, if lambda gets smaller, delta V is going to get larger. So as lambda goes to zero, so when lambda goes to zero, delta V is going to go to infinity. And then part F wants to know, well, what happens if we send lambda to infinity? It approaches a large number without bounds. Well, if lambda goes to infinity, as lambda gets larger, delta V is going to get smaller. So as it goes to infinity, delta V is going to go to zero. And thus is the nature of being inversely proportional to one another.